Okay, so we'll go ahead and start off with this presentation here for Math 110. This is going to be, after this, we'll have 4 final countdown events remaining. So I'll go ahead and hand this off to Roberta. Let me just go ahead and we'll be live streaming this on Facebook. So students, you can be able to watch it there too.
Good morning. My name is Roberta Ayu. I'm the professional math tutor from the Shiprock Learning Center. And today we're going to be talking about exponents and logarithms. And in this presentation, we'll be covering the properties of exponents, exponential functions, logarithmic functions, natural logarithms, composite functions, and inverse functions. My first set of slides is about the exponential functions. And in this, we're going to cover properties of exponents, converting to exponential form, solving exponential functions, properties of the graph of the exponential function. Here are the properties of exponents. There's the negative exponent rule. B raised to the negative n is equal to b over n raised to the n. And here's an example of how we use that negative exponent rule. 5 raised to the negative 3 is equal to 1 over 5 over 3, which is equal to 1 over 125. Then we have the zero exponent rule. A raised to the 0 is equal to 1. So in my example, 7 raised to the 0 is equal to 1, or a negative 5 raised to the 0 is equal to the negative 1. The reason why this is different from the others because all we're looking at is the 5, not the negative. So we'll just carry the negative over and you'll raise the 5 to 0 and you'll get a 1. Then the product rule where b is raised to the m times b raised to the n is equal to b m plus n. An example again, 2 raised to the 2 times 2 raised to the 3 is equal to 2 raised to the 2 plus 3. And we combine those terms, we get 2 to the 5, which is 32. Then we have the power rule. A raised to the m, both of those raised to the n, and we write it as equals a mn. The example of that is x negative 3 raised to the 4 equal to x raised to the 3 times 4, which is equal to negative 12. And then we'll go back to the negative exponent rule of 1 over x to the 12th. And don't be afraid to combine these rules together to get to your simplified answer. And then we'll continue with the quotient rule of b raised to the m over b raised to the n equal to m, or b m raised to the m minus n. An example, b raised to the 3 over b raised to the 7, which is equal to b raised to the 3 minus 7 equal to b minus 4. And again, we'll go back to the previous rule of 1 over b raised to the 4th. And then we have the products raised to powers. So we have a times b raised to the n. We separate them, distribute the n to each term, which will be a raised to the n times b raised to the n. And in my example, we'll go with negative 2b raised to the 4th. So we have negative 2 raised to the 4th and b raised to the 4th. We get 16 b raised to the 4th You have the quotient raised to powers. That'll be a over b raised to the m. Distribute the m to each variable. So we get a raised to the m over b raised to the m. And the as long as b does not equal to 0. So your denominator cannot equal to 0. An example of 2 over 5 raised to the 4th. So 2 to the 4th over 5 to the 4th equal to 16 over 625. Exponential functions. Let a be a real number. The function defined by the equation f of x equals a raised to the x, where a is greater than 0 and a cannot equal to 1, is an exponential function. Here are the properties of the exponentials. Let x and y be real numbers, a and b be positive real numbers, with a not equaling to 1 and b not equaling to 1. So the first one is a raised to the x is equal to a raised to the y, if and only if x and x is equal to y. So the second one is a raised to the x equal to b raised to the x, if and only if a equals b. In this slide, we're going to cover how to convert to exponential form. So here is a raised to the x equal to y. And then here is x equal to the log base of a of y. The exponent of x on this side is the same as the x over here. And then the base a is the same as the log base of a. So here's an example of the conversion. Log base of a of 3 equal to x. So your x here will become the exponent of a, the base of a, exponent x is equal to 3. The second example is log base 8 of 4 equals to 2/3. 8 is your base, 2/3 is your exponent, and then your and your y is 4. So if you were to input this into your calculator, so a raised to the 2/3 should come out to 4. How to solve exponential functions. There is 5 steps. First, you convert your equation to exponential form. Then you write both sides of your equation with the same base, if possible. Then you write a new equation by setting the exponents equal, and then you solve the equation and you check your answer. Find the numerical value of x. X equals the log base of 2 of 16. 2 is your base, x is your exponent, equal that to your 16. Here, I did the equal both sides to the same base. On the left side of my equal sign, there's a 2x, that's your base. And on the right side for the 16, 2, I made 2 the base and I raised it to the 4th, which will give me 16. Since your bases are the same, you're just going to equal your exponents to each other. So x equals 4. So your answer is x equals 4. We put that 4 back into your 2 raised to the x equal to 16. And you get 4 equal to 16. You get 16 is equal to 16. And the second equation example is a log base 4 of x equal to the 1/2. Your base is 4. Your exponent is 1/2 equal to x. I plugged this into my calculator and I got 2 equals x. And then you can check your answer by putting this back into your log with your calculator. It should come out the same. Here are the properties of the graph of f of x equals to a raised to the x. When a is greater than 1, your domain of your equation of your graph will go from negative infinity to positive infinity. And your range will be only in the upper quadrants of your graph, so from 0 to infinity. We have no x-intercepts because it's only going it's only in the first and the second quadrant. And then your y-intercept is at 0 and 1. And it contains 1 1a, and negative 1 and 1 over a. And then your asymptote is your x-axis, which is this down here. And then the line y equals 0. So when it's and then your basic shape, it's increasing. So you go from here to there. Here's the properties. Here's another property of the graph. When a is greater than 0, but less than 1, our domain is still negative infinity to positive infinity, and our range is still in the upper 2 quadrants from 0 to infinity. We still have no x-intercepts, and we have the 0, 1 as our y-intercept. And our points are still 1a and negative 1, 1 over a. And our asymptote is still x, the x-axis, and the line y equals 0. And our shape is decreasing. So it's going from here into your negative, so it's decreasing. Here's an example of graphing an exponential function. Here are your steps. You're going to use the point plotting to graph. And then you're going to draw your graph by connecting your points. You're going to use your function. Our function today is f of x equals to 4x, 4 raised to the x. So f of x equals 4 raised to the x, and then we have your x points. So you're just going to pick some numbers. I usually pick about 5 numbers. So you go with a negative 3/2, which is 1.5, a negative 1, 0, 1, and a negative or a positive 3/2. Plug that into put your x value into the x, solve the equation, you get a 1/8, a 1/4, a 1, a 4, and an 8. And then just plot the graph. Here we can cover the natural base of e. It is defined as the value of 1 plus 1 over n, all of that raised to the n. As n increases without bound, that's the same thing as saying as n approaches infinity. And here is the approximation for the number for e. It's like 2.71828 ... Here's a graph of the natural exponential function. When you plot or when you input this into just e raised to the x in your calculator, and you should just get this basic form. And this one, the domain is from negative infinity to positive infinity, and the range is always in the upper two quadrants from 0 to positive infinity. Here's a self-check. Recommend doing a self-check after every section of your textbook or your homework, so you understand. In this section, we'll be talking about the logarithmic functions. We're going to go over converting to logarithmic form, solving logarithmic functions, the properties of the graph of a logarithmic function, natural log function, and the common log functions. Just some basic information about log functions. Let a, x, and y be real numbers. A is greater than 0 and a not equal to 1. That satisfies the exponential equation of a raised to the x equal to y. Then x is the logarithm base a of y, and the equivalent log equation is x equals the log base of a of y. Here is how to convert to logarithmic form. It is just the same as the exponential form, but you'll be going back into reverse, so they both interchange with each other. So my first example is 1/2 raised to the 4th equals to 1/16. So your exponent 4 will go on one side of the equal sign, and you go equals the log, 1/2 is your base, and then to the 1/16. I'm sorry, I didn't put it in a second equation. How to solve logarithmic functions. These are the simple steps of solving the function. Convert your equation to exponential function. Then solve the quadratic. You can also rewrite with the same base, just like solving your exponential functions. And then the base of log functions must be positive, so we eliminate negative. My first example is log base of x of 36 is equal to 2. So we're going to convert it to your exponential function. X raised to the 2 is equal to 36. Took the square root of both sides and got x equals plus and minus 6. Because these have to stay positive, we do not use the negative 6. And all we're using is just the positive 6 to solve our equation. So therefore, the log base of 6 of 36 is equal to 2. In the second equation, the log base of 1/2 of 1/8 is equal to x. So 1/2 raised to the x equals to 1/8. Here, I rewrote the equation to have the same base. So 1/2 base with 1/2 base for the 1/8 and raise it to the 3rd, which gave me 1/8. And then I just equal the exponents to each other. So x equals 3. So therefore, the log base of 1/2 of 1/8 is equal to 3. Now, this is how you solve the logarithmic functions without a calculator. So you set the equation, the expression equal to x, and then you change to exponential form. You rewrite it, and you simplify your exponents with the same base the exponents must be equal, and then you solve your equation. So my example is log base 9 of 3. I equal that to x. Got the exponential form, 9 raised to the x equal 3. Had a base of 3 on the right side. That is raised to the 1, and made the other side a base of 3 squared, since 9 is 3 squared, to the x. Used my properties of exponents and got 3 raised to the 2x equals 3 to the 1. And then because my base are the same, equals my exponents to each other, so 2x minus 1. Solved for x, and I got x equals to 1/2. Therefore, the log base of 9 equals to 3 of 3 is equal to 1/2. So that's how you solve the logarithmic without a calculator. Here's the properties of the graph of f of x equals the log base of a of x. When a is greater than 1, your domain is from 0 to positive infinity. So your domain is only in your right side of your quadrants of the y-axis. And your range is from negative infinity to positive infinity. You have no x, or you have an x-intercept of 1, 0, and then you have no y-intercepts. And then your points contain a, your asymptote is your y-axis, and it is increased, so from the negative to the positive. Here's the properties of the graph of f of x log base of x. When a is less than 0, or when a is greater than 0 and less than 1, your domain is the same from 0 to positive infinity. Your range is from negative infinity to positive infinity. Your x-intercept is 1, 0. You have no y-intercepts, and your points contain a1 and 1 over a and negative 1. And your asymptote is your y-axis, and then your basic shape is decreasing from positive to negative. This was a natural log function. The log function with base e is called the natural log. And the function f of x equals the natural log of x is the natural log base with e, where x is greater than 0. So y equals the natural log of x is equivalent to x equals e raised to the y. Here's your common log function. When the base of the logarithm function is 10, we call it the common logarithmic function, and the base is not shown. If the base a of a logarithm is not shown, we assume it is 10. The function f of x equals log x is the common logarithmic function with base 10, where x is greater than 0. So y equals log x is equivalent to x equals 10 raised to the y. Excuse me. Here is the example of how to graphing a logarithmic function. It is the same as the exponential form. So you're going to convert it to exponential form. Then you're going to do the plot pointing, and then you're going to graph by connecting the points. So you're going to have a y column, and then your x equals 2 raised to the y. Choose about 5 points. And then we solve your y points. You substitute it in for y, and you solve for x. So here's the function, the graph of the function. Here are the properties of logarithms. The blue at the top is your basic. So log base of a of 1 is equal to 0. Then your log base of a is equal to 1. Here's an example of that. So log base of 8 of 1 is always any number you stick in here, or term or letters or whatever you stick in there will always come up to 0. And then when your log base of 6 then it will always equal to 1. Here's your property, inverse property. For a greater than 0, x greater than 0, and a not equal to 1. A raised to the log base of a to the x is equal to x. And then log base of a raised to the x is x. So here's an example. 4 raised to the log base 4 of 9 is equal to 9. If you could see the pattern, the x here is the x here. The 9 is the 9 here. So the log base of 3 of 3 raised to the 5th is equal to 5. So your x here is equal to the x here, your 5. Here's the product property. If m is greater than 0, n is greater than 0, a is greater than 0, and a is not equal to 1, then log base a of m times n is equal to the log base a of m plus log base a of n. And here's our examples of that. I did 2 examples. One with log base 3 of 7x, and did the product property. Log base 3 of 7 plus log base 3 of x. This example here is log base 4 of 64xy, which is equal to the log base 4 of 64 plus log base 4 of x plus log base 4 of y. That is equal to, I plug log, if you do your equal the log base 4 of 64 equal to x, solve for x, and you get 3. So you get 3 plus log base of 4 of x plus log base 4 of y. Here's a self-check of all the logarithmics function. In this set of slides, we're going to talk about the composite functions. A composite of function f and g written as f of g and is defined by by this identity is read as f of g of x. Find and evaluate the composite of these functions. So f of x equals x minus 4, and g of x equals x squared. So we're going to plug we're going to start with your x, and then we're going to go with the g of x equals to x squared. Input that in, we'll get x squared. Then we're going to input f of x equals x minus 4, and then we get the f of g of x, and we're going to have an output of x squared minus 4. And our answer is x squared minus 4. Okay, the next few slides these are gonna show that however way you're doing your composite, you will not get the same answer. So this is where f of g of x is x squared minus 4. Your my second example is of g of x, g of x is equal to, when we put it when we're composing the two together, then we get x minus 4 squared. And then the third is where we think it's saying f times g of x, where we're going f of x times g of x, and the answer is, this is where we're just multiplying the two equations into each other. We're not combining them like the other two steps are. So that will be x cubed minus 4x squared. Next slide is the inverse functions. If f of x is a one-to-one function whose ordered pairs are in the form of x, y, then its inverse function, f inverse of y, is the set of ordered pairs y, x. So the inverse function, basic definition is f inverse of f of x equal to x for all x in the domain of f. F of f inverse x equals to x for all x in the domain of f inverse. So here we're going to verify that f of x equals 5x minus 1 and g of x equals x minus 1 over 5 are inverse functions. So first we're going to do g of f of x is equal to x. So we're going to do g, and we're going to put f of x in there, so 5x minus 1. Then we're going to put this into g. So 5x minus 1 will go in for x here, of the x minus 1 over 5. As you can see that the ones, the negative one and positive one, will cancel each other out, and we get 5x over 5 is equal to x. The 5's cancel, and we get x minus x. X equals x, I'm sorry. And this second part, we're going to go with f of g of x equals to x. So here we're going to put g into f of x. So x1 over 5 will go in for x. So 5 times 1x plus 1 over 5 equal to 1 equals to x. 5 cancels. So you get x plus 1 minus 1. The 1's go away, cancel each other out, and we get x minus x. So these are just saying that both of these functions are an inverse of one another. Here is the steps for doing the switch and solve strategy. This is how you find the inverse of a function. One, you're going to substitute y for f of x. You're going to interchange your variables of x and y. You're going to solve for y, and then you're going to substitute f inverse of x for y. Then you're going to verify that the functions are inverses by going through your composite of g of f of x equal to x and f of g of x equal to x. So my example is f of x equals to 4x minus 7. We substituted like what y equals 4x plus 7. Interchange the variables, put the x equals to 4y plus 7. Solve for y by subtracting 7 to both sides, and then I divided 4 from both sides, and I got y equals 7 or x minus 7 over 4, and then I changed my y to the f inverse of x. And then to verify, you would need to go through your composites. And then here is the self-check for the composite and the inverse. Here are the sources that I used, and this is the end of my presentation. If you have any questions, we are available at the through the Learning Center website or email. So thank you.
Okay, thank you, Roberta, for presenting your presentation. I truly enjoyed it. Do we have any questions for Roberta while I'm uploading the link for the evaluation surveys?